Okay, so hi guys, welcome to the last tutorial of this term. So today we're gonna talk about perceptrons, and we'll implement a simple classifier with both Pytorch and Keras and TensorFlow. So in the first one, we'll first go into the perceptrons. I'll first share my screen. Do you see this? Okay.
Yeah.
So Jake, how was the perceptron notebook? How was it?
Yeah, I thought it was all right. I got the hang of it in the end. I don't think I had any problems with it really.
Mm-hmm.
I think the only problem I really had in this notebook this set of notebooks at all was I had some problems with getting I think it was Keras to work, but that's not this notebook.
Right. Okay. So, I mean, this session 4 will not be something that is really serious. It's just a perceptron and a simple implementation of digit recognition. And thanks to the Facebook and Google researchers, we can use the wonderful frameworks. So it will be fairly easy and straightforward. So we'll go to the NumPy implementation of perceptrons. So as you could remember from the previous sessions, um, you can remember the logistic regression, right? And in the logistic regression notebook, I have mentioned that logistic regression, a single logistic regression unit, can be said also as a single layer perceptron. If you look at this perceptron diagram, we have n number of inputs, and then we have weights multiplied accordingly, and then we sum them all up and we input them into the activation function, maybe a sigmoid or ReLU or something else. And then the output is something called A. So we're just gonna implement a very, very simple activation function like a Heaviside step function. If y is less than or equal to 0, it just returns 0, and otherwise it just returns 1. So it's just a Heaviside step function like a step like this. And then the AND gate. So in the AND gate, I'm inputting 0, 0, 0, 1, 1, 0, and 1, 1. With this input, we can implement the AND gate by this, and you can actually, for AND gate, OR gate, and NAND gate, you can tweak the values of W's and B, the weights and bias. And then by doing so, you can easily get the results of AND, OR, and NAND of these inputs. So that will look like this. OR gate, the result of it, you get ones unless you don't have, if you don't have ones in the input. The NAND, it's a not and is you get one only if you get one. So it's very simple logic gates. But you could do these gates with a single neuron. But if you have tried implementing an XOR gate with just this single neuron, you could not do it. And there's a secret behind it. Because if you graph it, like the inputs in this plane, for 0, 0, you put black dot here, and you for 1, 0 and 0, 1, you have to output 0 for AND, and you have to output 1 for this OR, and you have to output 1 for this white dots. In the XOR plane, can you draw a line between, can you draw a line that separates white and black dots? That's impossible, right? In this graph and in this graph, it is linearly separable. But this graph in the XOR part, it is not linearly separable. So that is why you cannot do, cannot make an XOR gate using just a single neuron. So to do the XOR gate, you need to use multiple gates. You need to use NAND gate and put input also in the OR gate, and you have to end the NAND and OR so that in this way, you can implement the XOR gate.
Cool, we can see now.
Yeah, so yeah, those are separable and these are unseparable. And we can go further into these. We have added another neuron, right? And we can think of this as we're adding another dimension. Okay, we are adding another dimension to it. So here we were working with just single dimension, and here by adding another layer of neuron, we are augmenting the dimension. So if you remember the kernel method, it's really similar to the kernel method. And you can view this problem as similar to that one. So by augmenting the dimension, you can push up the white dots into the another level, and then it will make, and then so that we can make a hyperplane that separates the black dot and white dots. Okay. So nothing but a logistic regression. This was not provided in the problem notebook. I just added a few cells. And this was from this website, CNTK. It's a high-level API for various machine learning tasks. So the single binary classification logistic regression is just it's nothing but a single neuron, as you can see. And in the multi-class LR, if you use a different activation function called softmax, you can put the output, you can range the output from 0 to 1 so that you can predict the multi-class outputs. And we will discuss this later in the notebook, the MNIST one. We're inputting 784 pixels into the logistic regression function, and after the softmax classification, we can output 10 different probabilistic outputs so that we can choose what's the number of the picture. Okay, so can you tell the shape of a matrix of these or like these? So the shape thing is quite important in learning deep learning, I guess. So in the single neuron, if we let the inputs, if you have like 10 inputs, the matrix form of that is 10 by 1. And the weight, because we have only one neuron, the shape of it would be 1 by 10, and the bias, we're just adding 1, so 1 by 1. And the prediction is also 1 by 1, and the answer is 1 by 1. The neural nets, like here, if we have 3 inputs, the input is, as you said right here, is 3 by 1, and the weight in the first hidden layer is 4 by 3. The 4 means the 4 nodes of this hidden layer 1 and the 3 inputs. And here we have 4 by 4 shape, and here we have 1 by 4 shape, right? And the bias will always have 1 in the y, I mean, in this position, 4 by 1 and 4 by 1. Okay, and we're gonna look at the activation functions. So far we have seen only, I guess, softmax. Well, no, I guess sigmoid, right? While we're doing logistic regression, but there are several other activation functions that is really useful. So it is softmax, sigmoid, tanh, relu. There are other more activation functions, but we're going to look at these. So the softmax it's not drawn here, but it is really similar to the sigmoid function, and it's changed the outputs from the 0 to 1 output. And the sigmoid is quite similar, and tanh, if you look at the green one, it's -1 to 1, and relu is just a simple maximum 0, x. So it's less than 0. The input is less than 0. It just ignores it. And then you get the same input as the y value. Okay, that was it. And there's one open question here. So why do we need activation function? Can't we just make neural network without activation? So this question, I also had this question while I was learning like neural networks for the first time. But if you don't use activation function, it's just a combination of, it's just a linear combination, right? So here, if you have these and don't have activation function, we have x1, x2, and x3, and we have weight 1, weight 2, and weight 3, and weight 4, right? Here, we just multiply these and multiply these again, and then just output the single value. We're just doing a linear combination. But in order to do some complex tasks like XOR or other, really complex tasks, we need to learn a non-linear space, not just a single space like an AND or a problem. So that's why we are using the activation functions to make the combination, to like add non-linearity to the combination. Okay, let's move on to MNIST. Before that, do you have any questions?
None from me.
Right. Cool. Okay. The next one is digit recognition. So actually, after completing this notebook, you'll be able to join the Kaggle competition and finish that with good results. So that was this one I was talking about, the Kaggle digit recognizer. This is just a simple tutorial competition, not a real, like a legit competition, but you can still submit it and go to the leaderboard to check your score. So here, I'm first importing these and then, setting the path and X train and Y train from the data I've got. And here, I'm normalizing the data set. We've seen this a lot of times before in the previous notebooks, so you know why we are doing this, and reshaping it. And then this one, to categorical, it just, since we have a categorical values, we are inputting, we are changing the training set to the categorical values. So number of classes, we have 10 digits, so I've set it to 10. Right, so the shape, we have 37800, this number of training set, and then this is the shape of the single input. From the thing we've learned before, using the Keras, we can structure, construct this structure. We can first set the model with the sequential, and then by adding some other things into the sequential method, sequential variable, we can make a model. First, we're going to flatten it. The flatten means that we're going to literally flatten all the pixel values into the 784 single vector. And then this dense layer means we have 2506, 256 neurons in the first layer, and then 1 to 8, and then lastly we have 10 dense layer at the last, because we have 10 digits. So that's why we have 10 dense layer in the final layer. And note that here we're using ReLU in the hidden layer and softmax in the last layer, because maybe this is just a rule of thumb. We use ReLU in the hidden layer and softmax in the last layer. But the reason why is that the ReLU, it usually performs well during the hidden layer, in the hidden layers, and we're using softmax because we're classifying it. Remember, we had to make a range of outputs from 0 to 1 with the probabilistic values. Okay, so I've put CNN models here, like with conv2D filters and paddings and different kernel size, and also I've added some dropouts. But I wrote this for the guidelines for you to do, but maybe you can think of this as a topics for future notebooks. So in this tutorial, I'm not gonna explain deeply about convolutional filters or anything, but you can get this. This is your main takeaway from this notebook, right? So using Keras is really simple. So by doing that, you have to set your optimizer, and then not in Pytorch, in TensorFlow, you have to compile the model. And the loss, we are using cross entropy loss, like you've learned in the logistic regression. And for the metrics, we're using accuracy. Right. And we set the epochs. You don't have to set the batch size here, but it's optional. Here, callback, I'm using early stopping. So sometimes maybe your loss graph would look like this. And if I set epochs equal to like 100, the loss value will just stay in this value forever. So it's just a waste of computing resources. So you would want to stop earlier in this level. So that's why I'm using early stopping. Okay, and then you just call the fit method like the scikit-learn, and then you will get the results. And also, additionally, you can save your model maybe into the .h5 format, or or just a single file format, and you can call your model with Keras too. In Pytorch or Keras. That's a really nice method. Okay, and then from this history, you can get your literally history, and then you can plot it, and you can diagnose your model, how your model is doing, like this. The validation loss is decreasing, the accuracy is increasing, absolutely the loss is decreasing and into this value. And when you predict, you can just do model.predict, right? And then I've visualized the numbers and the answers because we have around 99% of accuracy. We are hitting it right. Okay. So this was it. Quite simple, right?
Oh, thanks, Danny. One point on early stopping, it's not only better for computation, it's also useful for not overfitting things. So if we continue to train, our loss may continue to go down, but our validation accuracy may actually go down as well, because we're paying too much attention to like all the details in the training data, whereas we only want to find the patterns that generalize well to unseed data.
Right. that was a really good point.
Cool.
Okay, so can we go to the Pytorch side?
Yeah, thank you.
Yeah.
So if I do, is it this one? Wait, I think this one. So can you see test loader equals none?
Yes.
Yeah. Cool. Wait, is that the correct? Yeah, it is a screen that I'm scrolling up and down, right?
Mm-hmm.
Okay. All right. So yeah, we saw how to implement neural networks with Keras. Now let's look at how to implement them with Pytorch. So it should be fairly straightforward to understand what's happening here. We need to install the dependency. We need to import the relevant things. So the first task we had to do here was to look at how we import the training data and import the test data with a slightly different rule of not shuffling the test data. We want to preserve the test data in the same order so that when we're debugging things, we don't get like a different sample. Should have been fairly straightforward to see how this should generalize. You just have the same parameters as before, but you set shuffle to false. So let me actually run these cells. I have this installed already, so just run this, run this. Cool. So this loader object deals with iterators. In particular, you have to create a iterator from it, and the way you query iterators is by calling next on them. You can also run through them as if you're running through like a list in a for loop. So they're special objects that take some time getting used to, but are like very efficient in the way they're implemented. All right, so let's look at what our data is. We've seen it from Danny's notebook already. It's just 100 and digits, 28 by 28, and here like just 4 of them randomly. And each one has an associated label, which is just what the digit in the picture is. Cool. So we have just a couple of things that we need to do. The first thing is to define our model. This model should be very similar, if not equivalent, to the one you saw in Keras. So there we had like 64 units and then 32 units followed, like hidden sizes of those respective sizes. So slightly differently from Keras, you here have to provide both the input dimension and the output dimension. So there is some repetition that has to happen here, but it shouldn't be not too difficult to find out how to change these things so that you get this. And you may have noticed that here we actually assign class fields to these objects. So this in itself doesn't do anything. It's just that later on we'll be calling these functions on the data, so we transform the data. So this is again slightly different from how things in Keras was done. Is here you have each of your layers as member fields of your class that you invoked in the forward method. The forward method gets called whenever we have something like this, where we've created our object and we call it as if we call a function, we automatically call the forward method of this class as long as we inherit the NN module class. Cool. So here we want to do the flattening that we did before. A reminder, our image is 28 by 28. We want to make them just like 784 values in a vector. So we achieve that by calling the view function. And here we were given how to do the first layer of the fully connected or affine layer, which we define here, and then the nonlinearity. And we were told to do that for the second layer. So again, fairly straightforward. We should just do this. And this completes our model definition. Now, if you compare it against what we had in Keras, you would have expected to have something like this here. Before returning the output, you would have expected to get a submix of this, such that you get this vector that sums up to 1. But we don't do that for reasons that will come apparent in a second. So the only other thing that we needed to do is define the optimization process. So the way we do that is we define a loss. We've talked about, like, in classification, we'll very often do a cross entropy loss. So you just need to be able to, like, call the correct function here. And by the way, the documentation for Pytorch is really nice. I'm very happy with it. And the other thing you need to define is the optimizer, which is just a standard stochastic gradient descent optimizer. You pass just the parameters of whatever you're optimizing, which for the deep, for the, like, neural network things will always be net dot parameters, and then you set a learning rate. Now you're given the option, or sort of the small exercise of fiddling with the learning rate and setting it to be either too small or too large. Jake, did you have the time to play around with this?
I haven't had the chance to play around with it properly yet.
So what you should have found is that if you set the learning rate to be too small, if you're remembering the equations of how we update the parameters, then our parameters will basically not change with each iteration. So our model will stay more or less the same. Now, the more interesting thing happens if you set your learning rate to be too high. That means that you're going in the direction of the gradient with a very big step size. And what you should have observed here is that your model actually starts performing worse and worse. This is called, like, the divergent gradient problem of sort of the worse your model becomes, the larger your gradients are. And if you're further, like, multiplying by 10, you're making bigger and bigger step sizes. So if you ever experience your model actually starting to do worse and worse, this is one of the reasons why this is happening. Your learning rate is actually too big, and you need to make it smaller. You'll notice that different learning rates, that for different models there are different learning rates that are appropriate, and there's no sort of one fits all selection for this hyperparameter. Here we are given something sensible. So the only thing we need to do is define the training loop. Now, this can look quite daunting at first, but it's actually really, really straightforward, and it does not change between model definitions at all. Cool. So what we do is we have defined our train loader. As I mentioned before, is this iterator objects here that I can just loop over as I would list or something like that. The enumerate function, in case you haven't seen it before, just assigns an index to each thing that you loop over. And then the data contains both our inputs and our labels. And then we just do a sequence of, what is it, like 6 steps that are, again, going to be more or less the same no matter what your model is. So the first thing you need to do is to zero out the gradients in the optimizer. So this is something very peculiar for Pytorch, in that Pytorch does not automatically, after each step, forget what the gradients are from that step. So you need to manually do this, which is quite nice for more complex models, but it's also like a source of mistakes for a lot of beginners, just because if you don't zero out your gradients, they're actually going to be accumulating in the background. Like, as you get new data points, you're just adding to the previous gradients, and then you're going to run into the divergent gradient problem that we were talking about before. So you're pretty safe just, if you're not sure what you're doing, you're pretty safe in just doing this before, like, following the following steps whenever you're dealing with Pytorch. Now, as I said before, this just involves the forward method, which is the actual inference that the network does, the actual prediction, the forward pass. And here I can show you another nice property of Pytorch, which is that it's all dynamically generated, such that if I run it before, if I run this, I can actually put a breakpoint. This is how you can put a breakpoint in a notebook, and I can actually query these things. So, like, outputs here, I can see what it looks like. And if you remember, we were expecting to get things of dimension 10. So you notice that this is 4 different things of dimension. Then why 4? Well, we set our mini batch to be 4, so we'll expect 4 data points at a time. But we don't get numbers between 0 and 1. We get numbers that actually can range from -infinity to +infinity. So this is exactly because we don't have the softmax thing here. Now, this is another sort of peculiarity of Pytorch, and it is because the criterion, the cross-entropy loss, here expects for us to pass the things before softmax. So it actually incorporates both the softmax computation and the subsequent cross-entropy loss in this function. This is something that's documented in the actual documentation, but it's something that can get you quite confused in why your model doesn't work in the way it does. In the way that it should, sorry. Now we know about this. We pass the labels. We pass the labels as just digits rather than one-hot encoded vectors, because again, this thing automatically does it for us. And we get a loss object that we're only ever going to go backwards on to propagate the gradients. So again, this is just slightly different convention that allows you a lot more flexibility. But for the standard models that we're going to be looking, it's just like this sequence of 4 steps will always be more or less the same. Or I should say 5 steps, because this is just calling the optimizer on the computed gradients and telling it to change the parameters using the optimizer defined here. Cool. So these are all the steps here. I don't think we have to do anything. I can just run it for a bit. And it's gonna train for a bit. While that's doing it, we can talk about model saving and loading, which is incredibly straightforward. As you can see here, like saving the model is just torch.save with the network, well, a method of the network that is more or less always the same. And then loading the thing is just going to be providing the correct path here. I think we're running this for 20,000, maybe. Oh, we're going to be running for 2 things, so it's going to take some time to cool. So we're going to save and load our model and then go on to testing our train model. We don't necessarily need to do this. We can just continue with the model we already have. This is just to show that, you know, saving and loading the model is actually really straightforward and fast. And this should be done. Yep. So we can save our model, we can load it, and now we have the same network that we had before in the loaded object. Cool. So testing here, quite similar syntax to what we wanted to do for training. Here we were taught to take the first 4 images, which is just doing this again. And we can check what these look like. They're very similar to what we had in the training paper here. And now, using our training net, we can actually predict on the images. And we see that our predictions are the same as the ground truth, which means that our classifier has generalized. One point to make here is the Torch-Nograd syntax that we see here. Whenever we want to use our network without having the intention of computing it, we should add this as a block beforehand, such that it uses less memory, is faster, and does not accumulate those gradients that we may forget to zero out. The prediction that we get from our output is those vectors that sum to 1. So if you want to get the thing that our network is most confident in predicting, we just take the maximum out of those. So I think very straightforward stuff for the most part. I think the last thing we wanted to do was to do some statistics for our network, which I think I'll just copy this whole thing. Yours, yeah. So actually, let's run to this. you're given the sort of scaffolding in order to compute the accuracy of the network overall, and then you have to create a way to compute it per class. And the way to do that is just whenever we predict something, we pick the associated, or rather, sorry. So we get the correct things, and then for each of the class, we iterate over and see if it's of that class, such that we can split things. There is nothing neural network about this, but it's quite useful to do a lot of these analyses, as we've talked before, because you may find that certain classes are easier to predict than other classes, and it can then help you change your network appropriately. Finally, note on doing things on the GPU is there is a one-time sort of overhead of needing to set up all the necessary libraries that you require such that you can run things on the GPU. But once you do that, and I've done it here, it's like doing things on the GPU is as easy as calling a method or two. So now these objects actually live on the GPU, and I can perform my computation on the GPU, which should speed up things significantly. Yeah, so this notebook really didn't require any sort of creativity in executing. If there are any questions, please feel free to ask them.
I don't have any questions.
Cool. All right. So then we can finish slightly earlier. Cool. All right. Any last words?
Okay. So thank you guys for joining our last session in the last term. We're looking forward to join with you and code with you guys in the next term as well. And this tutorial will be continued, as I mentioned in the README on the GitHub. So, yep, stay tuned.
Yeah. Merry Christmas, guys.
Merry Christmas.
Merry Christmas.
Merry Christmas.
Happy New Year.